In the atomic theory, this is our introduction to it, and atomic pudding. We'll talk about what that means in a little bit. Hopefully you guys got a little bit of that in the notes last class, which I'll probably check next class. So our objectives are, we need to understand the different atomic models. You guys don't have to take this all down. If you want, you guys can do an outline, and I'll post it later, and you guys can take a look. I'll tell you a few things that are going to be important to definitely take down. So we should also understand specifically the development of the Thomsom and Rutherford models, the plum pudding model, and the nuclear model. We should be able to explain the results of those experiments and figure out how we came to the big advancements in those and how we know that. We should also be able to identify the models based on their descriptions, and we should be able to place them in order of time or chronological order. So those are objectives. That's what we want to get out of this. Okay? Moving forward. The first people that really came up with the idea of the atoms were the Greeks, the ancient Greeks. And they just came up with the idea. They're like, oh, it was the continuous versus discontinuous theory of matter. And they just thought that everything could be broken down into elements. And they thought the elements were earth, wind, fire, and water. Here, these are the symbols for it. And there's a Greek philosopher named Democritus. He is attributed with coming with the idea of democracy. Essentially, his idea of democracy was very different than our current idea. I believe it was only male landowners had the right to vote. So, I mean, but he came up with the idea of it, similar to what we have today, but we have everybody can vote. And he came up with the idea of the atoms. He essentially said that there was the smallest piece of matter, and you couldn't keep on dividing matter up. You could only get to a certain point until it was indivisible. And that's where we came up with the word atom, the Greek word atomos. Okay? So, they didn't test this. There was no experiments. Back in ancient Greece, what did they do? They debated. They talked about it. Blah, blah, blah. And it wasn't a society like we are today. So they debated the continuous versus discontinuous theory of matter. And they argued. The Greek system, it was a hierarchy. So basically, if you were more popular, you were the one who was correct. That was it. Which wasn't very good, so they didn't test anything. There was no experiments. There was no science involved in this. So Aristotle, his continuous theory of matter was, he was the more famous philosopher, and he said that, okay, this is what it is, and then it was that for a long time. And his ideas carried on through the Middle Ages. So, alchemy. Alchemy is the precursor to chemistry. So the whole idea of alchemy was that they tried to take cheap, ordinary, household, crappy metals and turn them into gold. And they also wore funny pants. They really didn't understand a lot of things about modern chemistry, but they did do a few important things. Their whole goal was to make things turn into gold, because gold was expensive, and also make magical potions. So this is more of like a Harry Potter, kind of stuff. Really didn't work too well. They did come up with a couple things, like they knew about certain metals, but they thought you could change one element into another element, which we really can't do in a chemical reaction. So what they did was they were able to do some things, but they were probably isolating things from a mixture versus actually changing them into a different element. So they did do a couple things. They found some elements and some properties of elements. They also had some different techniques that we use, similar to ones we use today. Here's some what they did. So this is our timeline. I like that sound effect. Pretty good. Okay. So from the ancient Greeks up until the Middle Ages, nothing really happened in chemistry. I know. Sad. Okay? So, until John Dalton, a chemistry teacher in England, in the late 1700s, he took a lot of different experiments from different people all around his country and elsewhere, and put them all together. And he found, he came up with the idea of his, which is closest to the modern idea. It was the modern idea at the time, excuse me. So, Dalton's atomic theory consisted of three different things. The law of conservation of mass, where mass isn't created or destroyed in a chemical reaction. The law of definite proportions, also referred to the law of constant composition. And that's where no matter how much of a compound you have, it always has the same ratio of the elements. So no matter how much water you have, the ratio of hydrogen to oxygen is going to be constant. And the law of multiple proportions, where the law that states if there's two compounds made of the exact same elements, that the mass ratios of the masses in the compound, of the elements in the compounds, are going to be a whole number compared to the mass ratios in another substance, in that other substance. So what I really care about here is the first two laws we're going to talk about, and the last one is in the SAT sort of AP sort of topic. So why don't you guys copy these down right here? These three laws were integral in making what modern chemistry is today. And it explains a lot about the world around us. So conservation of mass. Here's a little diagram explaining it. So, for instance, if we start off with basically what it says is no atoms are lost in a chemical reaction. So if we start off with a certain number of hydrogen atoms, you're going to end up with that same number of hydrogen atoms. Start off with a certain number of oxygen atoms, you're going to end up with that same number of oxygen atoms. So here, if we start off with 385 grams of total mass, and we react, well, we will have 385 total grams after the fact. Okay? Does that make sense? And you can kind of look at it. If you start off with 4 oxygen atoms and 4 hydrogen atoms, you're going to end up with 4 oxygen atoms and 4 hydrogen atoms. Maybe not, they're not going to be in the same groupings, but you'll have the same number of atoms. In chemical reactions, we transfer the atoms. We'll talk more about this later. So, Dalton's atomic theory basically said that elements were consisted of atoms, and that atoms of the same mass were the same atom. That's actually not true, but at that point he had no way of testing otherwise. So that's how he identified them. So he said, Dalton kind of envisioned atoms like Legos. We all played with Legos, right? Yep, Legos are awesome. And if you didn't, go play with them tonight. That's your homework, in addition to the other homework. So, Miss Flannery, he envisioned them like Legos. And if you could imagine an object constructed of Legos, how much can you take those apart? You can only take those apart to the individual Lego, right? And that's it. Those are the basic building blocks of a Lego structure, are the individual Legos. And I like to think of the Legos as atoms. And different size Legos are just representing the different elements. So that's kind of what it's like. And for our purposes, we can think about atoms like that. Okay, for most things. But we didn't. But we know for a fact that there's more than just, atoms are just more than just solid spheres. And we'll talk about that as we move on. So, Dalton said each element had a different mass. Later proved to be not true. He said that compounds consisted of atoms with different elements combined. And he said that basically that the atom was just an indivisible particle. the basic building block. And each element had a unique behavior, which is pretty much true. The only thing is that it's not by mass. We'll talk about what later. So we decided, scientists, not we, I had nothing to do with it. They wanted to know if there's more to atoms than just, solid, little tiny pieces of solid and whatnot. So they tried to think of, was there something else that made up an atom? Listen up, guys. Look up here, guys. Look up here. Look up here. So it wasn't until the late 1800s when we had enough technology to figure stuff out. And we had, here's a summative slide. If you guys want to take a look at that later, feel free. Okay, that sums up Dalton's atomic theory. Thomson. Thomson was an English physicist, studied physics and chemistry and all sorts of things. He made a piece of equipment called the cathode ray tube. You are familiar with these because of the old, how we have the flat screen TVs now? You know the old TVs that have the long back? Yeah. That's similar to a cathode ray tube. You have these long tubes that project light onto something, the screen, like the monitor right here. There's these tubes that project light somewhere. So that's a cathode ray tube. It's a vacuum tube. They suck out as much air as possible. And what they do was, in this cathode ray tube, here, I have a little simulation here. I'll show you guys.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence, or bright light.
And that's what we see in TV.
When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate-bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons.
All right. So, moving forward, we saw a little simulation. Here's another little diagram that I made. It's not as good as that one. But you have the negative and positive charge plates, and when you have an electric current, it goes directly to it. When you add your electric field, they're drawn to the positive plate, indicating that the beam is made of negatively charged particles. So, there we go. There's another little diagram. I didn't make this one, I took it. So, if it's charged to a positive charged particle, it must have a negative charge. So, the cathode ray, later what they found out, it was a beam of electrons. So Thomson found out that all atoms have these little electrons, and they can be made to emit them. So, since there was no positive overall charge, there's no overall charge of an atom, he figured out there must be another charge balancing that out. So it must be a positive charge and a negative charge balancing it out. So he came up with the idea of the plum pudding model. I call it the chocolate chip cookie model. The plum pudding model. Plum pudding is a fruit cake-like dessert found in Old England where there's not even plums in them. I don't know why they call it plum pudding. But they have currants in like a gelatinous substance. It's kind of gross. I don't like it. But I like to think about it like a chocolate chip cookie. Imagine a chocolate chip cookie. You have your cookie background, and you have your chocolate chips in there. The chocolate chips are like the electrons. The cookie is the positive part. Okay? So, let's see. So he thought the electrons were like currants in plum pudding. A currant is like a little raisin. So that's the plum pudding model. It wasn't until Rutherford, Ernst Rutherford, was a very famous physicist who studied with Thomson. He noticed that when he shot these little alpha particles are very small particles. They're actually a nucleus of a helium atom. Sometimes when he shot them through air that they were deflected. So he figured there has to be something there that's deflecting them. He did one of the most beautiful experiments ever conducted, the gold foil experiment, where he had a very thin piece of gold foil, a few atoms thick. He had a alpha emitter, which was uranium, and a fluorescent screen which would detect where the alpha particle landed. So he expected that the alpha particles would just go straight through because there's the atom was, wasn't very dense. He thought it was going to be kind of like shooting a bullet through a chocolate chip cookie. It's going to go right through, right? But and he thought that because he thought that the mass was evenly distributed amongst the entire atom. Expected to go right through. Here, let's hear that again. So what he got was that some of them went through. Some of them were deflected. Some of them were deflected a lot. Some of them bounced back. He's like, what? That's crazy. He was so shocked by this. What Rutherford said, can you sit down normally? Actually, he didn't say that, but just sit down normally. What Rutherford said was, it was kind of like if you took a piece of paper, shot a bullet through it, and it bounced back. That's what he was that surprised. So what we found out, so he thought originally that it would just be able to go through because of an even mass distribution. So he thought that the beams would just go through. But what happened was, most of them did go through. But some of them were bounced back, so they must have hit something very massive and very dense. And that's where we came up with the nuclear model of the atom. So what those alpha particles that were deflected were bouncing back, they hit that very dense part of the atom called the nucleus. The nucleus of the atom is very small compared to the overall size of the atom. So it's an analogy would be like if you had a quarter on the 50-yard line of Gillette Stadium, the quarter would be the nucleus, and the whole atom would be the stadium. The nucleus of an atom is very different from the nucleus of a cell. I know you guys studied that in bio. If you were an atom in the nucleus of the cell, your atom, the nucleus of the atom would be the quarter at the 50-yard line. The atom itself would take up the stadium, and the cell, the nucleus of the cell would be like the entire state of Massachusetts. So the nucleus of an atom is huge. It's very, very tiny compared to the nucleus of a cell. The nucleus of a cell is so much bigger. Okay? So just to get that point across, we're talking about much, much different scales. You can see the nucleus of a cell. It's like it's a few microns, I think. A few microns. This nucleus of an atom, we're talking about tenths of a nanometer or something like that. So wicked, wicked, wicked tiny. So Rutherford's atom was the nuclear. So most of the particles actually empty space. Let me sit up. And this just sums it up. So the big mass in the middle occupies a very small amount of space. So if you have a big mass in a small space, huge, dense part of the atom known as the nucleus. So that's what we had until Niels Bohr, a very funny-looking gentleman in his old age. He came up with the next atomic theory of the planetary model, which you guys talked about, I believe, in 8th grade physical science, where you had the nucleus in the middle and then the atoms at a specific energy level. And you guys talked about this, like 2 atoms in the first energy level, 8 electrons in the second energy level, 18 in the third energy level, 32 in the fourth. Yeah, that's kind of okay. We're going to learn something a little more than that. But what he said was that they could go between those energy levels, so that the electrons could go up an energy level, down an energy level, but they are always in a specific orbit. So the Bohr model here there's a little diagram about it. Take a look at this afterwards. I have a summative slide at the end of it if you guys want to pause it and take a look at it later. So, the planetary model, here's another one. It's all right. Well, I don't really like it too much because the quantum mechanical model explains so much more about how everything works in the world. Quantum mechanical model was that you had your dense nucleus, but the electrons weren't in orbit. I'm not going to get into how we actually found this because the Schrodinger equation is quite complicated, and I have to teach you calculus first, and that would take the whole year of chemistry, so I can't really do that yet. You guys, when you get to, after you take calculus, you guys can go to college and study how they came up with the thing. But what the quantum mechanical, Bohr and Einstein, two real dumb guys, they were thinking about how they interacted and how they were inside the atom. And what they found out that electrons weren't specifically confined. What he found out was that there was more of a probability of where they were likely to be found. Kind of like me. Say that Mr. Kilgore is an electron, right? And my orbital is B108. That's where I'm most likely found, right? If you're looking for me, where are you going to come? Am I here all the time? Thank you. So I'm not here 100% of the time. I teach a class over in C116. I go to the teacher's room to eat lunch. Sometimes I go to the office. Sometimes I even go to the restroom. So I'm not 100% of the time in here. But my most probable location is in this room. So that's like my orbital. Okay? Does that make sense? So that's how and we're going to learn more about that as we go on. Here's a little schematic about all the different models and how they came up. If you guys want, take a look at this tonight. I know they're kind of tough to draw. But you should know like the order in which they came up and whatnot, and kind of the big developments, especially the Thomson and the Rutherfords, because those are easily understandable for us without having to learn calculus. There's our modern view. This is something that you guys want to take down. Most of the atom is made of empty space. The electron, the nucleus has the protons and neutrons, and the electrons are in orbitals. Most probable location of being found. Here's some the models. The Greek models, they're like the billiard ball model, Dalton's model, the plum pudding model, or chocolate chip cookie model, Rutherford's model, the nuclear model, Bohr model, the planetary, and the quantum mechanical model there. And these are objectives again. I'll leave those up on the board for a second so we can take a look at so we knew everything what we're doing.